Hello, my name is William Stearns, and I'll be talking about our project, covers the composites and their use in construction of helicopter rotor blades. Helicopter rotor blades are used to generate lift in helicopters as well as thrust. They contain aerofoils, which, when rotated by the main engines of the helicopter, generate this lift by creating differential pressure across the blades. This creates a force across the blades, and that is the primary form of loading for these helicopter blades. The force across the blades occurs in the z direction, thus requiring a higher flex modulus. This force is directly proportional to the takeoff weight of the vessel, and as this vessel's size and weight increases, the amount of flex modulus also increases. Additionally, to generate forward or aft thrust, the vessel must bank, and this further reduces the aerofoil area to generate lift, increasing the amount of force required on those particularly exposed areas. Additionally, as weight is a critical factor in aircraft, this converts the modulus to a specific modulus. Also, as the blades are exposed to the elements, they must be able to resist water and wind and sand erosion due to their operating conditions when they're a wide range of temperatures as well. Given their exposure to environmental conditions and repeated cyclic loading, helicopter blades must be well designed in order to ensure a long operating life. Helicopter blades can last as long as the actual vessel themselves, however, this is highly unlikely in most scenarios, and generally they operate for a few thousand flight hours before being replaced in an overhaul. Another factor of importance is the ability of the blades to attenuate vibrations. Have a limited capacity to attenuate vibrations in flight, and thus a reduction in the blades is a significant benefit. Another factor is the noise produced by the blades themselves. As most helicopters operate in civilian areas, the amount of noise pollution generated is a significant byproduct. Lastly, the application has cost implications for the materials to be used. Civilian blades typically range in price from approximately 1.5 to 3,000 per pair. However, more complicated applications may increase the price and the cost allowance of the blades up towards of $500,000 for Apache helicopter blades.
Rotor blades were originally made with plywood sheets glued together. These were a poor choice as they would become ruined by water and eventually deform. Aluminum, stainless steel, and titanium were tried next, and they all have good specific strengths and stiffnesses, but had high costs and weight. So, these materials have been replaced by composites. Composites have appropriate specific strengths and specific stiffnesses as needed for the blades. Glass fiber, aramid fiber, or carbon fiber are all used with epoxy depending on the cost and ability of the blades desired. Composites are better choices than metals because they have greater fatigue strengths, are more available, have much lighter weight, are easier to shape, are reliably reproduced, fit the aerodynamic and vibrational needs, resist corrosion, and have gradual failings instead of catastrophic. Of the three composites considered, each has its own benefits. Benefits to choosing fiberglass are that it has a high strength-to-weight ratio, good environmental resistance, and good flexibility. Aramid fibers are durable and have high tensile strength. Carbon fibers, meanwhile, are versatile and can be used in other parts of the helicopter, are stiffer so that they have better turbulent airflow resistance, and have a high modulus to withstand high flexural loads, but they are much more expensive. In the case of military helicopters, carbon fiber and epoxy will be the composite of choice for the rotor blades.
The purpose behind design features of the rotor blade is maximizing strength while minimizing weight. The part is made with longer composite fibers running along the length of the part to keep the same strength throughout. The fibers have a resin matrix but are pre-impregnated instead of using a manufactured wet layup technique to make certain properties are uniform. The part is made with a sandwich structure using filled foam or honeycomb matrix. This increases the strength by absorbing energy when forces are applied as well as minimizing the weight. The spar is the space where a metal rod runs through the length of the blade when it is attached to the motor. Rotor blades are greatly affected by erosion because of wind resistance and sand or salt particles in air, so most rotor blades have a titanium erosion shield on the leading edge. To test the characteristics, static strain tests and dynamic strain tests are used. Static tests test the reaction of pressing forces along the blade and comparing how the part withstands those weights. Dynamic tests shake the part to mimic vibrations, measuring the structural response with sensors.
Helicopter rotor blades require a high modulus in the longitudinal direction, so high modulus carbon fibers are used. These fibers can either come from polyacrylonitrile or pitch, which is a petroleum byproduct. The fibers are formed by being pulled through ovens of increasing temperature where the outer functional groups are burnt off, leaving an almost 100% carbon structure. From there, the strands can be formed into pre-pegged sheets by pulling them through the resin bath, removing the excess resin, and placing the fibers onto a mat with a nonstick coating so it can be wound onto a larger spool. An alternative to forming pre-pegged sheets is to pull the fibers through resin for use in filament winding. Once the fibers are coated in resin, it's important for them to remain refrigerated so that curing doesn't happen too early. The helicopter rotor blade is made using a sandwich structure using either aluminum or aramid fiber honeycomb structure, with a laminate on either side. The honeycomb core is cut into its final shape using CNC machining techniques. Once that is done, it is laid in the mold along with several layers of resin and carbon fiber prepregs, and it is vacuum bagged and put into an autoclave for 5 hours. Rotor blades can also be assembled using filament winding. An advantage to this is that it is automatic and fibers can be aligned very carefully. To do this, the honeycomb structure inner core serves as the mandrel around which the fibers are wound. As the honeycomb core rotates, fibers are wound, ensuring complete coverage of the rotorcraft blade. Once the filament winding is complete, the part is sent to an oven where it has allowed time for the resin to cure. Once the blade exits the oven, it is a complete part ready for use in the field.
The cost was calculated using a length of 16 meters, a width of 1 meter, and a thickness of 5 centimeters for the honeycomb insert to find the volume, then the weight. This was added to the cost of other raw materials required. These prices do not account for the labor or equipment. Higher costs would come from labor for manual layup, machinery for filament winding, and autoclaving.